Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is Hybrid Materials Composite Fundamentals. In the last lecture, we discussed the following topics: the combined use of material property charts and material indices was introduced. In hybrid materials, we discussed the possibility and idea of hybridization. It was discussed that there are 4 different ways of hybridization, like best among all, arithmetic mean, harmonic mean, and the least of all. And finally, the concept of FGMs or functionally graded materials was briefly introduced. In this lecture, we will cover the following topics. In composite materials, first it will be discussed the design principle for stiffness at minimum mass, and also after that the design principle for minimizing thermal distortion in a composite material will be discussed. After that, it will be shown that how hybrid materials they fill up the holes in material property charts, and finally the advantages, limitations and applications of composite materials will be discussed in detail. The main keywords for this lecture are composites, stiffness, thermal distortion, advantages, disadvantages and applications of composite materials. So, whatever we have learned so far, we have learned that a composite material is actually a combination of any 2 materials. This can be either a metal and a ceramic, a polymer and a ceramic, and this can even be 2 ceramic materials together. And the composite materials, the constituents can have also different shapes and forms, like the reinforcement might have the shapes like particles, long fibers, short fibers, laminates, interpenetrating and so on. Also, we have learned that the interface between the matrix and the reinforcement plays a very important role, and the more detailed knowledge about the interface will be discussed in the future lectures. Further, we have shown that a composite material, although it is homogeneous in the macroscopic scale, microscopically the composite material is always inhomogeneous. Further, we learned that there is possibility to actually predict the properties of the composite materials. Now, in terms of predicting the composite materials properties, there are different ways. It can be either the prediction of the exact properties or can be approximate properties. Now, prediction of the exact properties of composite materials can be extremely challenging. This is mainly because of the fact that, as I already mentioned, composite materials are inherently heterogeneous materials, and as a result of that, it is extremely difficult to actually homogenize the particle distribution over the complete length scale of the sample. There are definitely methods like finite element models or methods like that, which actually assume some idealistic particle distribution. However, these are all idealistic, and in real scale the real microstructure is actually much more complicated than the model microstructure. So, a more feasible way is to actually find out the bounds for the properties. These bounds actually provide the boundaries, that means they actually define the hard bounds within which the composite materials properties must lie. There are different bounds have been proposed, like 2 bounds we briefly discussed yesterday. One is the upper bound or the Voigt bound, and the other one is the lower bound or the Royce bound. Again, these bounds will be discussed in more detail in future lectures dedicated solely to composite materials. Now, what is the function of these bounds? As I already mentioned, these bounds actually serve to provide brackets within which the composite properties will lie. That means, using these bounds one will not get the actual exact material properties, but knowing the composite materials constituent volume fractions and the particle distributions and particle shape, one can predict the approximate value of the composites properties. And for many applications for design purposes, this is a very efficient way, because this is cost effective and this is also simple and the bounds are well established. Now, there are different properties, and for different properties different bounds have been proposed. For this particular lecture, I will simply propose two different properties, because these are the properties of interest for this lecture. The first property is the density, and density, as you can see from the topmost portion of this slide. So, when a composite has two components, like one component is the matrix is the phase which is the continuous phase, which is the major phase, and the other one is the reinforcement phase, which is the phase that is distributed within the matrix. Now, if we assume that the reinforcement has a volume fraction of F, and if we assume that there is no porosity in the composite, that means that the matrix has a volume fraction of 1 minus F. And if we know the density of the reinforcement at the matrix, if they are rho r and rho m respectively, then the density of the composite is actually given exactly by this equation, F, that is the volume fraction of the reinforcement multiplied by the reinforcement density plus the volume fraction of the matrix multiplied by the matrix density, and this is an exact relation assuming there is no porosity in the composite. In terms of modulus, so Young's modulus is bounded by, as I already mentioned, so called upper bound and the lower bound. The upper bound is also called Voigt bound and the lower bound is also called Royce bound, named after the proposers of these equations. Now, if we again assume that E r is the composite materials reinforced Young's modulus and E m is the matrix Young's modulus, then the upper bound and the lower bound are given by the respective equations shown on this slide. Now, it is generally a convention for composites to actually refer to the composite property as a suffix C, to the reinforcement property using a suffix R or F, and the matrix property using a suffix of M. Now, as you can see, this upper bound is the arithmetic mean that we learned in the last lecture, and the lower bound is the harmonic mean we also learned in the last lecture. So, basically the idea is that whatever be the amount of the composite's reinforcement, whatever be the volume fraction, whatever be their orientation, whatever be their distribution, the modulus of the composites must lie within this upper bound and the lower bound if there is no other porosity or other phases present. So, with this basic knowledge, now we try to solve two different problems and see that how actually this material selection knowledge can actually lead to an optimum selection of the constituents of a composite material. Now, this is again very important, because as we learned in the so far in this lecture, that technically any combination of two materials can actually lead to a composite material. So, that automatically raises the question, can we simply take any material any two materials and simply build a composite out of them? But again, this is all function dependent, provided that it is possible to fabricate the composite material with any two materials that has been decided. It is important that the composite material should actually lead to improved properties over the bulk material properties from which the composite is being made. Now, in this slide actually I introduce again the Young's modulus over density plot, and the problem is that there is a beam which is currently made up of aluminum. That means, you can see at the bottom portion of this plot there is one orange circle which is showing the aluminum alloys, which is the current material of the beam, and now it is intended to actually obtain a material with improved properties. That means, we intend to develop a composite material which will give better properties over the current material of the beam, that is aluminum, and because the function is the beam, that means, as we already know that we have to have this material index parameter is e to the power half over rho. So, that means, the lines in this plot with slopes of 2 actually will give you the material index which has to be maximized. So, what is the way of our approach? So, there can be any material, or I mean theoretically we can combine any two materials to fabricate a composite material, and that is why in this particular diagram we take two different composite options. First, we fabricate a composite between aluminum and aluminum oxide, that is alumina, and another composite between aluminum and beryllium. So, you can see there is also one orange circle for alumina on the right hand side and also one circle for beryllium on the left hand side. Now, these circles, they are not arbitrarily chosen. These actually correspond to the properties of both alumina and beryllium, because this is a diagram of Young's modulus versus density. That means, the density of alumina is known, the density of beryllium is also known, also the Young's modulus of alumina is known, and also the Young's modulus of beryllium is also known. That means, if we simply identify those points and then we join them, we can actually obtain the composite materials property domains. Now, as we just already mentioned that the properties of the composites must lie within the upper bound and the lower bound. That means, this upper bound and the lower bound expressions have been provided here with this arithmetic mean and the harmonic mean. So, what we simply do here, we simply calculate these expressions, and this region which is bounded between the upper bound and the lower bound is actually the area within which the properties of the composites between alumina and aluminum or between alumina or between aluminum and beryllium must lie if a composite is fabricated between these two constituents. Now, what do we see from this plot? We automatically see that the two composites actually function very much differently. If we consider the composite between aluminum and alumina, we see that in the best possible case, the values that we obtain from the upper bound, that is assuming the fiber reinforced composites along the fiber direction, this is lying between the lines of 4 and 5 for the criterion of excellence, that is e to the power half over rho, that is the material index parameter. However, if we choose between aluminum and beryllium as the composite material, we automatically or we almost get much higher values, which is even lying between 9 and 10 for the criteria of excellence. That means, we automatically see that reinforcement of beryllium is actually giving us much improved properties than reinforcement of alumina in aluminum alloys. The question is, why is it so? The answer lies in the density values, because as you can see over here that the Young's modulus of both alumina and beryllium, they are more or less similar. However, the density of beryllium is significantly lower to the density of alumina. If we see the density of aluminum is around 2.7, and if we see the location of the two orange circles, the density of alumina is more than aluminum, whereas the density of beryllium is actually lower than aluminum. That means, if we are adding alumina in the aluminum matrix, the density actually increases, density of the composite actually increases over aluminum. However, because of beryllium's lower density, if we add beryllium in aluminum alloys, the density of the composite is actually lower than aluminum. And because the criterion of excellence is e to the power half over rho, this actually leads to a situation that beryllium addition will be much more beneficial to improve the composite for this beam application over a composite reinforced by alumina in aluminum matrix. So, the basic, a general conclusion that we can lead from this discussion is that for this kind of situation, the best combination of material is that which actually leads that the bubble or the shape of the orientation of the bubble should be actually more or less perpendicular to the lines of your excellence. That means, these are our lines of excellence. So, this is our lines of excellence. If we can see this line, this composite, this orientation of the aluminum beryllium composite is almost 90 degree, whereas this other one, this composite between your aluminum and alumina is at a much lower angle. So, the best property improvements are obtained for those conditions where the composite will actually lead to almost normal orientation with the property excellence lines, and this way we can again optimize the constituents of a composite to obtain the best properties. After this problem, the second problem that in our hand is that we want to fabricate a material, a composite material for thermal management applications. Currently 1000 series aluminum alloy as matrix is being used, and we have two different reinforcements as possibilities, either boron nitride and silicon carbide. So, again this material property chart, as you can see over here, it is a plot of expansion coefficient alpha along the y axis and thermal conductivity K or lambda along the x axis. So, what is the function of, or what is the requirement for thermal management application? In thermal management application, the most important point is to reduce or minimize the thermal distortion. The thermal distortion actually comes from temperature excursions, and because of that two factors are very important. One is to have the material should have a very high thermal conductivity, because if the thermal conductivity is high, then the temperature will be equilibrated over the whole material volume pretty fast. That will lead to less thermal gradient. And the second point is that the material should have a low CTE or thermal expansion coefficient, because a low expansion coefficient will lead to less amount of thermal strain, which will again lower the thermal distortion. So, again we have two properties at hand, and now we have to again see that how the selection of the composites constituents can actually optimize the thermal distortion or minimize the thermal distortion. So, again we just follow the same procedure as before, it is always the same procedure we have to follow. So, again we identify the 3 points or 3 circles, 3 orange circles in this plot. One for the matrix, that means we identify the points for the CTE and conductivity of the matrix. Then the two reinforcements that we have in our selection, that means the boron nitride and silicon carbide. And also we see that there are also trend lines plotted here. These trend lines again they correspond to a constant value of 10 to the power of the excellence criteria, which is lambda over alpha. So, as we already know, for lowest or to minimize the thermal distortion, the excellence criteria should be as high as possible. That means, the lambda over alpha should be as high as possible to give a minimum possible thermal distortion. And as we can automatically see that already silicon carbide is a much better material or reinforcement material for thermal distortion or to reduce thermal distortion over boron nitride. Why? Because silicon carbide has a higher thermal conductivity and lower expansion coefficient, whereas boron nitride has lower conductivity and higher expansion coefficient, and as a result a composite between aluminum and silicon carbide is more appropriate for reducing thermal distortion than a composite between aluminum alloys and boron nitride as a reinforcement. So, this way I have shown you two different options or opportunities of actually optimizing the composites properties by proper composites constituent selection. And believe me, this is a very important aspect whenever any hybrid material design is made, because in any case, as I already mentioned, there is infinite possibilities of fabricating a hybrid material. That means, the material selection is extremely important to actually identify which materials will provide the best combination of properties. In this slide, actually this is the last slide from this materials selection aspect, whatever I have been discussing for the last couple of lectures. So, we have from the very beginning we have been maintained we have maintained and we have specified several times that one of the fundamental importances of hybrid materials are that they actually fill up the holes in the material property charts. So, this slide again we use the Young's modulus over density chart for reference, and this chart will actually clarify this idea of hole filling in a more clear manner. So, as you can see, this slide is kind of an enlarged version of the original Young's modulus over density plot, and there you can see that we have this plot or this region for the polymers, and somewhere we have the regions somewhere we have the ceramics, because ceramics should be somewhere over here, because as we know that ceramics have higher Young's modulus or the highest Young's modulus, and density of ceramics should be even lower than metals. And here this is another batch, as you can oversee over here. So, this is actually the region of the metals. That means, we have one region or one bulk region for the polymers, the topmost bulk region is for the ceramics, and this bulk region is for the metals. If the hybrid materials had not been there, the rest of the plot would have been empty. But now, because we have the hybrid materials, these are the like your ceramic reinforced polymers, like fiber reinforced polymers and all those things. So, they actually fill up this region. Then the metal matrix composites between metal and ceramics, they also fill up these regions. So, this way we can actually fill up the void places in the material property charts by developing the hybrid materials. So, with this we have come to the end of the discussion over the material selection aspect and the design of the hybrid materials. Next, our next topic is more, now we will be getting more directly into the discussions of the composite materials and cellular materials, and we first start with the basic advantages and limitations of the composite materials. So, what are the primary advantages of composite materials? As we have already learnt, composite materials may actually provide us with a lighter weight, that means lower density than the bulk metals. If the reinforcement has a lower density than the matrix, the composite is expected to have a lower density. At the same time, the composite can provide us with higher stiffness and strength. That means, composites are ideal for high specific stiffness and strength. They also provide the ability to tailor the reinforcement architecture for improved strength and stiffness. That means, it gives us excellent flexibility. We have learned that we can have fiber reinforced composites or particle reinforced composites or laminates or short fibers, and they will have different combinations of strength and stiffness. Composites can also give us improved fatigue life and also improved corrosion resistance, but they are not free from limitations. One of the biggest limitations is that higher cost of raw materials and more expensive fabrication and maintenance. So, composites, because you need special environment for special fabrication, special equipment, sometimes the equipment are extremely expensive, you often need expensive raw materials like high quality powders, and all those things actually make the composite materials more expensive than the more cheaper or more economic bulk materials. That means, the use of composite materials is only apt or appropriate when you have a significant property enhancement. If the composite materials design is not resulting in a good property enhancement, there is no point in a composite materials development, because it will actually lead to a higher cost of the material. Apart from that, we have higher anisotropy. Then there can also be more susceptibility for impact damage and delamination. That means the interface between the metal and the ceramic or the matrix and the reinforcement also plays a very important role. And also repair work of composites is also significantly more challenging than metals, and also recycling is also one issue where composite materials actually suffer over the metals or the bulk materials. What are the fundamental applications of composite materials? There are many applications. So, some basic applications are being shown over here, like in many applications involving like aircraft, like military aircraft, and all those cases where lightweight, that means in any aircraft application low weight is a very important factor. That means any material with low weight and high specific stiffness and strength is ideal for aerospace applications or aircraft applications. And there are many applications like aircraft wings or blades and all those areas where composite materials play very important role for military aircraft development. Also passenger aircraft like Boeing 787, as you can see from this particular diagram, more than 50% of Boeing 787 is actually made up of composites. So, composites actually play a huge role in aerospace industry, and these long haul flights which are possible these days are also majorly due to the availability of more and more structural composites for aerospace design. Also for aerospace applications like for rockets, there are or supersonic aircrafts, there also composites play a very important role, because composites, apart from their high stiffness and low density, composites also have good thermal properties, and there are also other composites like some ceramic matrix composites, they have extremely high melting point, and by composite design the ceramic matrix composite actually can also increase the fracture toughness over the bulk monolithic ceramic, and this way these ceramic or ceramic composite tiles are excellent materials for protection of the metallic chassis of these aircraft components. Also in other automobile applications also, like is being shown in this particular slide, there are many parts in modern automobiles which actually depend upon the composite materials. These are mainly polymer matrix composites, but as we will see afterward, there are also composites where metal matrix composites, like in brake pads where friction actually plays a very important role, there also composites are extremely important applications. Also in many ship applications, or like in boat fabric, like in modern boat fabrication, where also lightweight plays a very important role, because in many sporting applications where speed is extremely important, or speed boats for example, for rescue boats, there also weight is extremely important, and composites actually again provide structures with low weight and high specific stiffness and strength, and these are again attractive criteria for these material design. Also, as is being shown over here, for many construction purposes also composites are very important. Again, this is a very important application of composites these days, because as we are suffering from global warming and we all look for alternating means of energy, actually wind energy plays a very important source of energy all over the world, and this is a renewable energy with unlimited resources, and these you can see that these are the windmills where these huge blades, they are actually made of the composite materials. And again you can see this HB plot, why these wing blades are made out of composite materials. Again these HB plots I have discussed several times. This is again because here again for this particular application the critical property is e to the power 1 by 2 over rho, and as we already discussed, for this specific property again composites outperform the bulk materials, and that explains that why the composite materials like polymer matrix composites or even natural materials like bamboo or wood, they are actually ideal materials for this kind of wind turbine applications. Many sporting applications these days depend upon the composite materials like the golf clubs, the tennis rackets, the bicycles, like these bicycle frames for the very lightweight bicycles for cross country racing, they are of carbon composites. They are extremely expensive, and but they are extremely lightweight, and this actually allows the biker to actually move over the mountain terrains or kind of rocky landscapes. And also for these speed boats, as is being shown over here, these are all examples where composites play very important roles. Then again, these are other applications of composites, like as I already mentioned, metal matrix composites for electronic components, like again one needs to minimize the thermal distortion, like optimize the thermal properties. Then ceramic matrix composites for the exhaust nozzles, where you have high temperatures like corrosive gases. Then carbon brakes for automobiles, and also for MMCs for many structural components applications. So, all these are applications of composites, where without composites we cannot think the modern technology. So, with this we come to the conclusion of today's lecture. In this lecture we have discussed that composite properties can be grouped by the upper and lower values, typically called the upper bounds and the lower bounds, and irrespective of the configuration and orientation of the reinforcements, the properties of the composites must lie within those upper bounds and the lower bounds. Then we also showed the methodologies for optimized selection of the composites constituents for different applications. Two such applications have been discussed, like a light stiff beam and for minimizing thermal distortion, but many such applications can be devised by as per requirement. And also at the last part of today's lecture, I discussed about the advantages, limitations and applications of composite materials for many advanced applications. These are the references from which the material for this lecture have been taken, and in the next lecture we will be discussing the introduction to metal forms and the application of metal forms for structural application, functional applications and architectural applications. Thank you very much.